Hello, I'm Billy Hoffman.
And I'm Matt Wood. Both of us work for the Web Security Research Group with HP Software. We used to be a company called Spy Dynamics when HP purchased us about 2 years ago. Mm-hmm. And so both Billy and I came up with the idea of, hey, let's what can we do cool with the browser? And that's basically what we're going to talk about today.
So just to get things out of the way real quick, what is a darknet? So kind of the definition we're using, it's a private network where users can freely exchange ideas and content. Darknets typically have additional features, things like strong encryption, digital identities, distributed storage systems, things like that.
So, that's a darknet, but what's actually happening in the browser space? What's happening with all of the technologies that people are using on the internet, right? So as we're seeing now, there's this new set of browser wars that's happening. Firefox really lit the fire under everyone else and really got the innovation going. And not only that, that brings a whole lot of cool new features, security features as well as, the fancy flashy features as well.
Right, this isn't the marquee tag again. Yeah. This is, nice powerful things, browser-based client-side storage, orders of magnitude faster JavaScript interpreters. And the nice thing is that all of the browsers, for the most part, are playing nice with these standards. So you no longer have kind of like an if, i.e. do all this stuff, otherwise do all of this stuff type development methodology.
And so you're really seeing a shift from the desktop, really. We've seen a lot of changes in the way people use their computers in terms of the technologies and what they're taking advantage of. So a really good example of that's Gmail. I mean, I'm sure everyone here has seen Gmail. Or you've probably used it, and it's my primary email. But I mean, so everyone's seeing that the web's really, really good for this basis of building all sorts of applications, and stuff like HTML5 is going to make it even better. And so beyond that, we're taking a look at how is the web evolving? Where is it actually going to go? And we've seen a lot of just changes from the standard server-client model. So what we're going to kind of talk about is, hey, why hasn't the traditional web browser really kind of gone to a more peer-to-peer kind of activities? So why aren't the clients talking more to each other? Why are we still just talking to the server?
Exactly. So obviously, we didn't come up with this stuff on our own. We're really standing on the shoulders of almost a decade's worth of work now in terms of things like Freenet, Waste from the Nullsoft guys, even some P2P networks like Gnutella and all the clones that have appeared. One thing, Roger is awesome, Tor is awesome. We're not Tor. We're not trying to undo or recreate Tor in any way. Tor is anonymized routing and can do anonymization of web traffic. A darknet is literally a private network on top of it. It is separate. It is not trying to help you anonymize your browsing. Use Tor, and Tor is very good at that.
So what are some of the barriers to people actually using something like Freenet or Gnutella?
Because we have these things out now. Why aren't people using them more?
Yeah, and really it has to do with just the technical challenges of actually using all of them. While people can go to the websites and download them, install them, and sure, it sort of works from there, but you have to configure your firewall to make sure everything works. You have to configure any kind of NATs that are in the way. Some guy on the street of New York City is not going to be able to use Freenet or Tor. And so what we're really trying to do is, attack the technical barriers and kind of attack at the same time the barriers that people are having, just, getting their friends to use technologies like this. So
exactly, a darknet of one is kind of boring. So you have to figure out, how do I get other people to use these? It really comes down to barriers. And the web ecosystem is really enabling all of this to happen. What we're going to be talking about is ways to drastically lower the barriers of participation. And the main features that have accomplished this are a lot of the HTML5 spec stuff, the fact that, TraceMonkey, Squirrelfish, V8. First of all, how great would it be to have your job be naming JavaScript, interpreters for these browsers? I love the names. The fact that we don't have to write a lot of existing, or we can leverage a lot of existing, very popular, very powerful JavaScript libraries.
Yeah, the open source movement has really just brought so much just code to the web, and since most of it's all just kind of scripting languages anyway, it's hard to hide what people are doing, and all of that code is really building on all of the stuff people have seen before. And what we're doing is just saying, hey, we need AES and we need RSA for JavaScript, so I'm going to go out to the internet and see if I can find that. Exactly. And I don't have to implement that myself because I would certainly screw it up.
Yeah, what is it? Thomas will kick us all in the nuts because we're using AES. Or we're typing it and we're not crypto guys. All right, so a browser-based darknet. Let's take some properties, let's take some pieces of these different types of networks, and let's kind of see what can we actually bring into the browser space. So what we really wanted was a way of having a distributed, redundant file storage system that's actually on the browser. We wanted to have some degree of anonymity and privacy. We thought about the web within a web. There's a fantastic security researcher out of Cambridge named Ross Anderson. Really, you should read his stuff. And he wrote a paper called The Eternity Service, where he was describing, is there a way that you can build a system so that you can publish content, and even if somebody held a gun to the person who wrote its head, there was no way they could unpublish it.
And so, I mean, if you look at these first three things we mentioned in the properties we want, really this is all the same thing that other darknets are really able to do, and pretty much do better than we're able to do. But what we wanted to accomplish was essentially get this into the browser and do this entirely over HTTP using just JavaScript and HTML and some server-side scripting.
Exactly, because if we move this to the browser, we get a whole lot of benefits. One, it's a zero footprint install. And really, the web client is the new web server. The HTML, I mean, the browser is no longer a dumb terminal rendering a document that was sent to it by the server. We're talking about having the client play a huge role, and the server really is just moving traffic around.
Yeah, especially with features like the web in the web. There actually is absolutely no storage on the server. All the server is doing is routing information between clients, and the clients are actually reassembling everything, displaying a web page, and it's almost like there's other servers on the darknet actually providing you with the content you're seeing.
Exactly. Another really great property is these things are very simple to create and tear down. So things, I hate using buzzwords like flash mobs and stuff like that, but it's very easy for you to create a network, use it, share content, tear it down. Why? Why would we even do this? Other than this is really cool and technical stuff, and we like to play with JavaScript and use it in ways it wasn't intended. But we very much believe any type of barrier is bad, and removing any type of barrier is a good thing. The fewer barriers there are allows more participation, and more participation means innovation. Matt and I are smart enough to realize we're not going to be able to do everything you could possibly do with this. If you think about content publishing, since Tim Berners-Lee created the first web server, anybody could create a web page. The cost or the barriers of entry in the early 90s was more likely than not having to set up your own web server, publishing the content, and actually getting it indexed.
Yeah, and then you get GeoCities coming around, and people are able to actually not have to set up their own servers. All they have to do is know how to use an FTP client and some HTML, and they can set up their own web pages. And then you have stuff coming around like MySpace and Facebook, where people don't even have to know HTML, or they don't even have to know what FTP is. All they need to do is type something into a text box and hit submit, and they've all of a sudden started publishing content on the internet. I mean, 90-year-old grandmothers can use blogs and publish stuff on the internet. This is not something that they were able to do, let alone 5 years ago.
Now, we're not saying that darknets are going to reach the popularity of some of this other stuff, but we're just saying, look, the trend of removing barriers always leads to innovation. When YouTube came out, I remember thinking, wow, this is going to be full of copyrighted material and porn. And true, but I doubt the creators of YouTube ever thought the president of the US would use it to address the nation or discuss policy. So, jumping in.
So what are we going to talk about today? We've kind of given you the background. So first we're going to give you just kind of really high-level architecture. So when I start doing the demo, you're not going to be totally lost. And what is he doing? It's magic up there. Then we're going to do a demo of kind of the prototype that we created of a browser-based darknet. Then we're going to go into just kind of the more technical overview after you've seen kind of the features work. And then we'll keep going into deeper dive into the actual stuff that we've been doing. So here's the high level architecture for you. It looks very much like standard server client paradigm, except now we've got servers connecting to other servers. So we're actually going to be able to peer servers to servers over HTTP, and literally that's just going to be a communication medium for all of the browsers that are up there.
For those of you who are familiar with, say, like a P2P decentralized network, you really can think of the browsers as nodes, the web servers as supernodes. And you can link supernodes together so that they can pass messages, and somebody who is a node on some distant supernode, if there's a connection through other supernodes to them, you can talk to them, and all of them can share information and data.
So without further ado.
There's a demo, yeah, it works.
Yeah, that's
okay.
Apache.
Questions?
It works great.
All right, we're done here. Let's get coffee.
All right, so I'm going to open up our demo here in two different browsers, just so you guys know that I'm not blowing smoke. All right, so this is Mozilla Firefox. I'm going to type in the username Firefox, just because that's going to be useful later. So you can see that you can specify a public and private key here, and this is in OpenSSL format.
We don't need to generate them.
And okay, so this is Safari now. So I'm going to type it into Safari, and again, you can see the public and private keys there. I just have those built in there because I don't want to have to go generate them from OpenSSL in front of you guys because I can't type very well. So the first thing I'm going to do is prove to you that these guys can actually communicate. So we have this thing called chat, and chat's the ability to essentially type in whatever you want and hit send, and it gets echoed back into the other client. So if I go back to Safari, it didn't show up. So I'm going to do it again. And hopefully this time it shows up on the other one. All right, there we go.
So one thing to note that we should probably show real fast is that these are actually running on two different servers. Firefox is connected to 192.168.80.1 or 80. What is it? 128.
That's why they didn't show up. I'm an idiot.
Oh, you were using the wrong one?
Yeah.
Okay.
All right, so what Billy's pointing out here is the URL is actually separate, and I used autocomplete to not actually connect.
So we see Safari here is on point 1, and Mozilla is going to be on point 1.2.
We'll name this guy Firefox 2. And I'll say hello, Black Hat. All right, and there we go. Now I've sent it a bunch of times to the other guy to make sure I got it across.
So that's not really sexy, right? I mean, you can do that with Gtalk. You're on the same server. Who really cares about that? Well, what we said is we can go ahead and start actually, just like in a regular P2P network, we're going to start joining supernodes. So if somebody is on a different server, we'll actually link those two servers together, and so that the messages can actually reach.
Yeah, so what I'm going to do here is join 168.80.1 to 168.80.128. And I'm going to establish that connection. And now, when I actually do this again, and send it across, it should show up in all of the windows. So now the routers are essentially joined together. And now, okay, so cool. We've talked about this really simple debugging mechanism that I've proven that I'm not going crazy. And so what can I do with this? Well, one of the things is a private chat. And private chat here essentially allows me to query the people who want to be found on the Darknet, and I can start communicating with them directly. So if I pick Safari, and I say, okay, let's start a private chat with Safari, and then I send it some information. I go to Safari and check that out. It's actually showing up in Safari here. And now, okay, that's cool. That's the same thing I just did, is it? No, it's a little bit different. What we've actually done is actually an entire private public key exchange there. And if I go to my debugging console, just start proving this to you guys, you can actually see here that we received some information from Safari here. This is Safari's public key. We then chose Safari and generated a secret AES key that we're going to then do some public key crypto on to get some to do the key exchange. And then this is the encrypted message using the AES key. So if we go to Safari and look at the other side of that communication channel, you'll actually see that, okay, we received a key exchange from Firefox. He's giving us his public key, and he's also giving us the encrypted message. So we're going to use our private key to decrypt the AES key, which is right there, and then we start talking via encrypted channel.
So a running theme in this talk is going to be poorly implemented protocol on top of HTTP. So we are doing a public-private key exchange. The reason we had some person we were showing say, why aren't you just using SSL? SSL is point-to-point. So from Matt's browser to 192.168.80.1, that is connected. But if then that server from Matt's connection maybe to my browser, that's a different setup. So the server will actually decrypt to plain text and then re-encrypt to push it back down the SSL connection. We don't want the server to be able to see anything. We want to end-to-end encryption. If anybody here deals with web services, this is a lot like XML encryption, which when you first hear about it, you're like, what, are you crazy? But then you understand that for end-to-end encryption, this is what you have to do.
And it's good to mention that all of that was done entirely in JavaScript. There was no plugins or anything associated with that. So what I'm going to do now is I'm going to upload a special file to the cloud that I created.
We should probably say, when you join the Darknet, kind of like Freenet has this property too, we are actually yielding, but it's a variable amount of space, whatever you want, but say 20 megs to a few hundred megs of space on the client-side system, on that web browser. And so Matt joins, and I join, and Caleb joins, and Joe joins. We now have 4 people on the Darknet. Each of them are sharing 20 megs. We have 80 megs of space. We have 40 gigs of redundant storage space inside. So if Matt wants to upload a file into the network, what happens is we can take this file, encrypt it, slice it into pieces, and store those pieces redundantly across all 4 of our systems. So that if Caleb, one of his many ladies calls and he's got to go, and he drops off the network, then we don't lose the slices. It was stored redundantly. And we can now actually pull that out. Are you going to join somebody else?
Yeah, so I'm joining Google Chrome to the network, and then I'm going to retrieve the file that I just uploaded into the Darknet.
Yes. Questions now, Toby. So once again, poorly implemented protocol on top of HTTP. We decided to keep it open and just build the infrastructure for doing the slicing. And right now we do a very basic put, just double it. And put, at any time, there is always 2 slices of a file on someone's system. We started to build a very primitive load balancing system so that if you have 3 people on a network, Caleb join, or one of them drops off, we were thinking that the slices, they either can get resliced and redistributed. We haven't implemented that part yet.
Yeah, we'll go further into each one of the features implementations after we do the demo.
You can see here that Matt over here in Chrome actually pulled up, and we didn't just go grab a lorem ipsum generator in JavaScript. You can see the
I put some random stuff in there.
Yes, the nice tresses. So we have, can you actually show the debug where we can see which, each client will be able to say, hey, I just got a slice of this file. And you actually can see that these little slices of these files are being stored in the client-side SQLite database that's accessible from JavaScript inside the browser.
Yeah, so right here is the actual storage that had happened in Firefox. Firefox actually received 2 pieces of this, piece 0 and piece 1. And basically that's telling it, hey, store that in your database. And then you'll see right here, it actually was asked to retrieve the files, and then it found piece 0 and piece 1, and then sent it back over to Chrome. And Chrome wasn't on the network before we did that.
You can almost kind of think of this in a way, it's not BitTorrent, but the idea that I can go ahead and pull slices from peers, and that multiple peers might have the same slices. We thought about building a checksum mechanism so that way when we reassemble the slices and display them, we can check against a checksum to make sure that Toby, because he's evil, didn't maliciously tamper with the slice. And then if, for example, Toby did tamper, we'll try the other slice and make sure that one's not tampered as well.
So the next thing I'm going to demo is the web in the web. So
well, before we go, we need to specify the way we actually said find me this file, we use the hash. So you take the file, and we did a hash of the file and said, okay, that's the identifier. Has anyone here heard of magnet URIs by chance? All right, I see some nodding heads. So magnet URIs are used in P2P networks. And it makes sense. A URI is supposed to be like, connect to this host and fetch me this resource. Well, that doesn't really work in a peer-to-peer network or a decentralized peer-to-peer network. So a magnet URI says, hey, decentralized network, I am looking for the resource that has this hash. If you have that resource, tell me. So it's kind of like an anycast, almost in a lot of ways like ARP. Tell me who has blank. And that's how we're actually able to get these things back.
Yeah, so I'm going to show you the HTML that I'm going to upload with the web in the web example here. Basically, it's really simple, just HTML, and you can see this magic JavaScript call here, which is actually going to give the magnet URI of the Lora Ipsum page. So I'm going to load this. I'm actually going to visit the magnet URI of this HTML page, and then I'm going to click on a link inside of that, and it's going to load up the Lora Ipsum one. So there's the link.
And you'll note the host we're still on is the Darknet. All we did is that we just did a document.write. That's why the client went away. So he's going to go ahead and actually fetch that file. And we're actually browsing a web file inside of the web and then clicking on a hyperlink to take us to another file.
So JavaScript did a little turning there, which is what froze, and then all of a sudden you've got lora ipsum being shown just from clicking on that link. So you can arbitrarily link between files with just using some of the fancy HTML stuff that we can get for free in the browser.
I want to make sure this point isn't lost because Matt and I tend to talk fast, and we're doing a lot of alt tabbing here. But we took a file, we encrypted it, and in this case, we went ahead and just encrypted it with an empty key so that anybody can essentially decrypt it. We went ahead and sliced it into pieces. We store these pieces redundantly across all of the people who have modern browsers that have access, where the JavaScript in the browser can access client-side storage, either a database or a name-value pair, a dictionary. We store these slices of the file on it, and we pulled them back and rendered it. But it's not just documents. We actually put a web page into the Darknet, and that web page hyperlinks to other things stored inside the Darknet. So we have literally built a World Wide Web that runs on top of the World Wide Web. And it's redundantly and persistently stored across the peers. So if somebody joins the Darknet, pushes several web pages in and disconnects, those web pages are persisted across the peers. And more importantly, the peers might not even know they have it. There's no way you can look at the little slices you have and understand what those files are, unless you happen to have all of them and you knew the key. So you essentially have hidden web documents that are now stored and scattered across multiple people's machines. And if you know the right command, you now can start visiting this entire separate private web. This is really where we drew inspiration from the Eternity service in terms of being able to publish something that, unless half the peers all drop without people coming in to replace them before it load balance, it's very difficult to unpublish this work. And everybody in the Darknet isn't even aware the work's been published, which I think is kind of cool. I don't know about you guys.
So going beyond just the web and the web, what else can you do with a whole bunch of browsers connected to each other? And so one of the stuff, Billy and I both loving JavaScript, probably too much, we're just like, hey, let's do distributed JavaScript jobs. Let's just send a bunch of JavaScript to all the clients.
Let's do SETI at home in JavaScript.
That's right. So we're going to do something really simple here just to show that it works. I'm going to tell all the clients, hey, tell me what 5 plus 5 is. So when I hit the distribute button here, it's going to go out to all the clients, and all the clients are going to say, hey, okay, here's all of my results. And we're all 10, surprise. So we could obviously keep going further with this and try to implement something we did with the private chat and say, hey, give me all of the peers, and then I'll build it's like an input to a JavaScript function. We'll then distribute jobs upon all of the peers. So you can keep building and building on this type of stuff.
There's actually a pretty cool, it doesn't seem to be still maintained, but there was a pretty cool JavaScript-based MD5 cracking program where all you did was just leave a tab of your browser open on a site, and it would pull down essentially small parts of hashes to crack, and was running in JavaScript, and it did all the jobbing and the reporting, and it would, it wouldn't just send one job, it would do it maybe to 2 or 3 in case the peers died. Obviously with a 5 plus 5, that's pretty basic. We're literally passing that code to eval, which goes against every fiber of my security being. Like, here's a block of code from someone you don't know on a network that is kind of private. Why don't you execute it?
There's stuff, we'll talk about specific ways and how we think you can combat that a little bit. But that was basically the demo. We showed you all the features that we wanted to show, kind of proved that we're not just kind of making all this stuff up when we're talking about it.
We can jump back as people have more questions.
Yeah, for sure.
Really, we want to kind of do, now that we thought it'd be a lot better to show you what we were talking about before we spend a long time describing these features and how they work.
Yeah, now you can put ideas to actual stuff that you saw. So what was the server we're connecting to? Well, we're calling that the router. And the router is essentially just a single dynamic server-side page. That's PHP, ASP, Python, Ruby, whatever you want to do it in. All it needs to do is provide a common connection to the client, have AJAX targets for the client to use to send information back to the server, and it needs to provide some kind of peering way between routers. So it needs to have HTTP, it needs to have URIs for all of those essentially.
Right.
And some kind of simple transient storage for holding messages temporarily.
So you can't have true peer-to-peer in a browser because there's no way for you inside of JavaScript yet to say, listen, accept connection. There are no abilities to listen on incoming sockets and fork off to handle it. So what we have to do is, because I cannot talk directly to Matt's browser, what I'm able to do is I kind of bounce the message through the server. The server is, in many ways, you can think of it as like multicast IP. Very basic. The client is really where the bulk of this is in terms of JavaScript, HTML. The content, this initial client is served to you by this PHP file, this router. So you would connect to it, get the client, Matt would connect to it, get the client, and now everything is on our systems. If I want to store, we just bounce the slices through the server.
And if you wanted to be really sexy, you would serve the client code from the Darknet. And so people wouldn't even have to be served by the router, it'd be served from the network itself. So basically some other stuff that the client is doing, and all it needs to have is an API for browser storage, some way for us to do local storage, whether that's with the Whatwig DBs or the local storage or...
Don't use cookies.
Don't use cookies. If you really have to, I guess you can. And then basically those JS encryption routines, we need to be able to do some kind of RSA and AES so we can provide private chat.
With those routers, do the JS encryption routines, do they keep it sort of compromised for routers compromised? That the whole network will be compromised?
Good question. We'll start talking about that as we get a little bit farther on. So the encryption because it's end-to-end, the router isn't going to be, you could do traffic analysis and say, this guy, node A who's connected to supernode/router, 1, and it's also connected over here. These people are talking. I'm not sure what they're saying because the encryption is actually done natively at my client before it goes into the network, and then at the other end, it's decrypted. And like we said, we use a public-private key to actually then, much like SSL, decide on, it's pretty much always AES 256, to pick a symmetric encryption algorithm to then use for the communication between those two peers.
So just some more vocab. I'm not sure how many of you are familiar exactly what comet is when we're saying that. Basically, when you do traditional HTTP, you request something from the server, and the server immediately gives you the response, and that's called, that's a pull request. You're pulling information from the server. What Comet's actually doing is kind of a cool hack. It's a mix between JavaScript and a really long open HTTP response. Essentially, what you do is you make a request to the server, and then the server says, okay, well, I'll just keep this open for minutes. And during those minutes, if I receive any events that I need to send to the client, I'll just send a chunked packet that has a script call, which will call back into the client and essentially act kind of like an event-based system there.
Right, so what would happen is that the browser, or the client, the veiled client, connects to the server and basically says, hey, open a connection to me. Open basically a really high bandwidth downstream connection. The server responds and says, hey, connection's open, it's going to be chunked, and then waits. And then sends maybe a period every now and then to basically keep that connection alive. So if the server gets a message and it needs to push it out, what it'll do is it'll basically push down something that just says, hey, here's a script tag. And the browser who's slowly downloading this chunked goes, hey, I just got a script tag. I can, because this is chunked, I can start interpreting this before I get the rest of the response that never ends. And so it basically starts executing that script tag, which contains the data, and it calls into the veiled client and says, hey, here's your packet. So that's how we kind of get this. Instead of having to pull, we have a push model that comes down.
So what are the ways that the clients are communicating and the routers are communicating to each other and the clients are communicating with the router? We talked about the basic stuff, but how is this actually happening? How are we actually accomplishing this in our Darknet? So when a client messages another client, this is actually using the protocol on top of HTTP essentially that we've built. And there's two types of messages. There's multicast, which goes to the entire network, and then there's obviously the router. And this is very much like the internet, and there's benefits of both. So what's the router-client communication, right? So the router, or the client needs to connect to the router. This is how you establish the first URI. You were doing the comet connection. We're essentially using a hidden iframe. First of all, we did that because it was easy, and it's simple. And it's also a little bit higher bandwidth than long polling requests. So the long polling request is just an AJAX call that sits on the server and waits for something. And then as soon as it comes back, it has to make a new one. So you have to keep reestablishing connections. So if you're sending a bunch of messages, a comet connection is a little bit better. And then the client uses AJAX to send messages to the router that's occurring on the client. And you would be silly not to use something like HTTP auth or SSL when you're connecting to the router. So you can use, we didn't actually use that in the example just because I didn't want to sit here and type in usernames and passwords all day long. But if you're implementing something like this and you want it to be more secure than, we're demoing, basically you want to make sure you're using SSL when you're connecting to the router so that no one's going to man in the middle of you.
At least on that part.
Yeah, at least on that part of it. So router-to-router peering. Of course, you should use HTTPS again. Basically, what happens is one router makes a connection to another, which establishes a reverse channel back. So this is very much kind of like the comment kind of paradigm, except we're not using any JS hacks. We're just using, PHP's fsock open and slowly reading data back, just like a normal system would, except because of HTTP, we don't actually be able to establish a bi-direction TCP connection. We're actually having to establish two connections from, the local side to the remote, and the remote has to say, oh, you establish a connection with me, and I'll have a connection with you, so he has to establish a connection back. So one of the problems with that is both the servers need to be mutually accessible. We'll talk about, maybe a way to get around that in the later part of the presentation.
Now, don't freak out about the performs routing. We're going to talk about this in a minute. These supernodes, they are not simple repeaters, like when I was saying IP multicast. They don't simply get a message and then they say, everybody who's connected to me, whether it's a client or another supernode, let me just rebroadcast that message. We tried to put a little bit of intelligence in it so that we would try to reduce essentially the traffic. That doesn't really scale very well as you add nodes where you're having to repeat it to everyone. And so we decided to use a little bit of the ad hoc on-demand distant vector, which is used by wireless mesh networks to do decentralized routing. It's fairly simple. We're running low on time, so we're not going to dive too much into it. We can talk to you about it afterwards, but really the only reason it's there is to try to help reduce the traffic to make this a little more scalable, and it minimizes clients receiving traffic that they weren't really meant to get. Now granted, it's encrypted, so it doesn't matter, but there's no reason for them to get it, so don't give it to them.
So let's actually talk more about how we implemented all of these features. So the global chat, that's just silly. That's just sending multicast packets to the entire network. The private chat, we'll go into that, and then the distributed file storage, the web and the web, all this stuff. And server failure we didn't even talk about yet, but basically that's a way for, what happens if one of the servers goes down and your client's connected to that server, what happens in that sort of situation. So the private chat, we do an RSA key exchange, like I said. We're actually using the PidCrypt.js library, so if anyone knows of a problem with that, they should let us know.
Now, here's kind of a cool aside. Right now, when you connect to Veiled, you had to supply your own public-private key. This is because we strove to say we don't want users to have to install anything to use it. If we added the requirement that they had to have Java installed, we could use an applet, which will give us access to the secure random number generator inside of Java, which means you can do key generation. We chose not to. Again, the Monsanto guys would kick us in the nuts because we don't know how to do cryptography, and we're not even going to try.
Yeah, so I mean, when you're talking over private chat, you're using AES, cipher block chaining. The really big thing about that is it's completely encrypted on the client. There's no server interaction and all of that. So whether the router's compromised or not, they're not going to be sniffing what you're able to do. And there is a possible man in the middle with the private chat, because when you do the RSA key exchange, if you have a malicious router that is able to change the public key, essentially they can man in the middle your public key there. And so you should always verify your public keys. I mean, using something like certificates, I mean, this isn't a problem that we're really going to be able to solve. I don't know if the browsers have really solved that either.
Well, exactly. It's again, we're trying to build the infrastructure to really allow clients to be very heavy, to all talk with each other, to store files and communicate securely. Everything else on top of that, reputation systems, secure identity systems, any of that other stuff, we don't want to try to solve because we know that we're probably going to screw it up. We'd rather discuss this publicly so you all can figure that stuff out. I'm looking at you, Toby, for that.
So the redundant distributed file storage, basically what we're doing is taking, we talked about this a lot before. Basically, we're taking files, we're uploading it to the router splits them across the network, and then we're using clients to store that information.
That's a good point, because here's the challenge. JavaScript cannot actually access local files. It can store things on the local file system, but there's no way to say, hey, let me touch this file. Even if you're using the HTML input of type file, you're invoking the OS file dialog select. JavaScript has no way of even accessing the contents of that file. So we can't do the slicing and encrypting on the client. So what happens is if you want to upload a file into the network, and if you optionally decide to crypt it, what happens is you have to send a message to the supernode you're connected to the server, just like you would with a normal HTTP multi-part post to do a file upload. You basically say, hey, server, here's the file, here's the key, slice. And we can tell it how many slices to put it in, things like that. At that point, it actually uploads the entire file in plain text. So the router does for a small period of time, have the entire file that you're uploading into the darknet in plain text. It then encrypts, slices, and then distributes the slices across the different clients.
But if we relaxed our plugin, desire not to have plugins, you could have Java doing all that stuff for you with a signed applet or something like that.
Exactly. A lot of photo sharing sites do that if you're doing mass file upload and things like that. They have a little applet that can do it.
Just to review basically what happens there. When you upload it, you select the file, it uses an upload, and you slice it into 1K chunks. It gets multicasted to the network. Say, hey, I need storage information. Tell me who can store this. We wait for the slices to be registered, and registered really just means some client has said, okay, I can store this information for you, and then that starts sending the specific packets to everyone on the network. Download is very similar. It makes a multicast request for, hey, here's my magnet URI. And tell me who has it. All the clients check their data stores, send that information back to the client that did the original request, and that's basically how we have that work.
That's the other end of the problem. So the client, the JavaScript client, gets all these slices, reassembles it, does the decryption itself. At that point, it now has a binary array, and it's like, okay, what do I do with this? In the case of the web within a web, it's a text file or an HTML file, and we could just write it into an iframe to display. If you wanted to do web within a web and have images, you'd have to use data URIs. So we can dynamically write it out. However, if you wanted to save like a Word document or a PDF or something like that to your system, there's no way JavaScript can invoke like, window dot save to local file system, here's a byte array.
That's probably a really good thing.
That probably is a really good thing. So what it has to do, again, just kind of as part of the upload part, it sends to the web server all of the unencrypted slices, just that one supernode, not all the supernodes, and says, hey, here's some bytes, and the server immediately turns around and gives it a content distribution header to say, save this, pop the little save as dialog in the browser, and refeeds the bytes back to you. So that way, the browser actually gives you the UI to access the local file system and save it.
So basically, the web just builds on top of the file distribution. We started talking about this. All you need is a magnet URI and then some JavaScript in the actual client to support some stuff like embedding images, embedding iframes, rewriting all of that code correctly, and just essentially taking that magnet URI, turning it into content that can be shown in the web pages. So distributed JS computation. Basically, like we said, this is just sending JS to a bunch of clients and getting the results reported back to you. Some of the dangers of that, like we started talking about, what about some dangerous JavaScript, cross-site scripting, that sort of stuff? What about threading, blocking on the UI? We're actually getting some cool stuff out of HTML5 called worker threads, which is going to allow us to essentially take any kind of working that has to occur that's not on the UI, move it off of the UI so that the web page is still pretty interactive. And then, so we started talking about, hey, there is XSS. What can we do? So there's this cool thing that Gareth Hayes is working on called JSReg, and it's essentially a sandbox inside of JavaScript. So it's a JavaScript sandbox inside of JavaScript. So it's actually using JavaScript to execute JavaScript that has been, correctly. Essentially, you have to use a special syntax, some syntactic sugar, but you're able to, essentially minimize what JavaScript's able to do in the browser.
So it prevents code from accessing things like eval or instantiating the prototype object, accessing the scope chain, being able to use the new constructor or the new function constructor or things like that.
So server failover, we didn't really talk about this one so much, but a good simple sample of this is what happens if you're connected to a server and then all of a sudden that server goes down for whatever reason, God strikes it down with lightning or something happens. You want to be able to still stay on the darknet. So what we've built in is the ability to say, hey, if one of the servers goes down, my clients are actually kind of keeping that common connection open, and also will check the server just to see if it's open every once in a while. If it ever goes down, if a server had been peered to it, it would have told all of the clients, hey, there's a new server on the darknet. You can, go connect to this if your current server fails. So as soon as you notice that your server goes down, you can go off to, the second server and say, hey, connect me to the darknet, make sure I still stay connected.
Now, we wanted to minimize what the supernodes knew. Our example was the supernodes are on a server. It's just a PHP file. It could be on a server that you compromised and stuck it there, or let me scratch that and say, a server, for whatever reason, you had the ability to stick arbitrary files on and execute them, whether they were your own or not. We said, so we can't really trust that. And so what happens is that when supernodes peer, like in this example, so let's say server 2 over there on the right, let's say it was connected to another server, server 3, server 1 doesn't know about it. The supernodes only know about the most immediate supernodes they're connected to. And so what would happen is that once you connect, server 1 tells its clients every now and then, hey, by the way, I know of 1 or 2 other supernodes. So if you ever can't talk to me, just reconnect to them, and you'll stay attached to the darknet. We actually came up with a really cool self-defense mechanism where if a PHP file detects that someone keeps trying to connect to me, but it's the wrong HTTP auth or something like that, someone keeps banging on me trying to get in, actually notify all the clients connected to you and say, hey, somebody's trying to break in, I am going to shut down. I'm going to disassociate myself from the darknet. By the way, here's the peer you should connect to. I'm shutting down in 30 seconds. And so all of the clients that were connected to server 1 would transparently jump to server 2. The best way to think about this, it's like a private club. You have to know where the door is. You have to know the secret handshake to get in. And if somebody is out there banging on the door and not getting in, the darknet kind of tells the other people, hey, we're just going to brick this door up. It's not going to work anymore, but don't worry, there's still a door around the back. And so the person who's trying to get in, they're not aware of that door, and they won't be able to continue banging.
Does the Darknet have the ability to blacklist supernodes without something like a brute force going on?
Right now, no. Again, that'd be a great way to implement. I believe LimeWire actually has they push out a list of blacklisted IPs to try to prevent people like MediaCentry and stuff from tampering them. You could do the same type of approach. Yeah. So that is the thing. We unfortunately are not able to release the source code for this. HP's been very supportive of our work. They have no desire to commercialize this technology. They, gave us their blessing pushing this out, and we're discussing in deep enough technical detail you can re-implement this yourselves. If not, come talk to us. We'll continue to talk about it in really technical detail. The process of going through to have us release the source code was longer than the time from when we got accepted to when Black Hat was. So we knew that we wouldn't be able to, in time, get through the process. It's not that we can't or wouldn't, it's just that we figured this is the easiest way to get the technical information into everybody's hands. Yeah?
Can individual users select which files they want to share and have access to, or is it everybody has everything?
No, so only things that are published. You cannot, as a client, say, I only want to have slices for these types of files.
Of the published things, of course. If I don't want it,
No, because you don't know what they are. It's just a hash, and it's an encrypted slice, and you have no idea what this is. So what would you blacklist? Like, don't give me a hash that has an F in it. Like, that would be kind of a cool way to, I guess, do it.
So we came across some challenges while we're developing this, and we figured it'd be good to at least talk about it. So when we're doing all these crazy connections with Comet, and there's 4 different clients connected to the same router, we actually end up doing threading on the server there, and we have to figure out what kind of stuff can the server-side languages give us that allows us to essentially lock resources in memory and don't allow anyone else to screw it up while we're trying to change a routing table or change the message queue or something like that.
I mean, think about how PHP is normally used. I make a request, the backend PHP language runs, generates a page, and gives it to me. We're talking about something that is constantly running in a big while loop and slowly streaming stuff down through a chunk connection. Meanwhile, on another thing, it's connected persistently to another server. I mean, you're essentially having a language that's supposed to run and execute and stop, constantly running, and you have multiple of these processes constantly running that need to share data through some type of shared data or shared memory or mutex system. This is a huge pain to debug.
Yeah. Another problem that we really ran into was the local storage versus global storage. So what happens when you do have a server failover where you actually do need to actually change servers, but that server's on a different domain? You actually end up losing all of the you essentially lose all of the slices that were on your client because that's all restricted by the domain. So if you change domains, you essentially lose the storage that was on the darknet. So that's
you lose the slices. The capacity is still there. You can just get the slices again.
Exactly.
Let's go down to advancements. We're going to skip through that. There are a lot of ways to attack this: malicious clients, malicious routers. We tried to solve some of the problems. You can look at the slides. I think we'd rather tell you about cool stuff to do with this than how to break it. Because I'm sure a lot of people can find flaws.
Yeah, so we started talking about, hey, what can we, the problem with peer routing is that both of the servers need to be mutually accessible. What happens if only one of them can talk to, there's only a one-way connection, like you're behind a NAT or something like that. So one of the things you can do is actually use a comet connection on the request. So instead of actually having the long pull and come back in the response, you connect with a request and the server keeps the request open for really, really long periods of time. And unfortunately, PHP isn't able to do this out of the box. There's a PECL extension, but we didn't want to have to rely on that. But essentially, you could do this sort of thing. Perl, luckily, does have it built in. So if you're a lover of Perl, you'll be able to make this work awesome. So this is one of essentially my favorite thing that we came up with that would be really cool to implement. I don't know if everyone realizes this, but we had file storage in the browser forever. We had this thing called the browser cache. And you can actually store, this browser stores images, it stores HTML files, it stores everything that the server tells it to store. And all you need to do is get a way to access it again. So what we're saying is, okay, so if you take a look at my horrible UML diagram here, basically what happens is the router says, hey, store this information for me, here's the hash associated with it. The client will then say, okay, I'm going to request a special URI that's unique to this hash, that goes right to the router. The router then says, okay, well, here's the data associated with that unique URI that you gave to me. And now that's stored in the cache because we sent down the correct cache headers and stuff like that.
Expires.
Exactly, all expires and all that stuff. And what happens when someone else wants to retrieve it later in time, the router will say, hey, I need this hash. The client will then say, here's an AJAX request with a special URI that I used before, and do I have anything in my browser cache, essentially? And if the browser cache does have something, the request will never actually go to the server, but it'll come back straight from the browser cache, and you'll get whatever response code you had before. But if it was a cache miss, essentially it goes to the server and the router and says, okay, I need this URI, but the router's like, this isn't something that I have. So it just gives
I asked you for this.
Yeah.
Don't ask me.
So it just gives you 500 error or something like that, and then you'll know whether you had it stored in your cache or not. And I mean, this is something that we thought was pretty cool, in that you could actually implement this on really old HTTP client or web clients.
Yeah, like you don't need HTML5. You need HTTP 1.0 for this to work. I don't really want to write JavaScript for Netscape 4.
So another thing we thought of is, what can we do to make this a little bit easier to join routers together? And why don't we just take the idea of a router and actually move the whole thing to the client? Can we actually use the client to do all the routing? And it actually turns out that you can with some of the new HTML5 features like X domain request and the CORS extension for Mozilla. You can actually request a separate domain as long as they give you the right header back. So you can actually open multiple connections to multiple routers. And if those routers weren't peered, your client can actually access as the router between those two separate servers. And really, this kind of all brings us next up to, how do we get rid of the router? Because this is a silly restraint. We don't really want that. What can we do, that would be cool to get rid of the router? And what we came up with is, hey, let's just use persistent XSS as a storage device. Because there's lots of stuff on the internet. The internet is really dirty. There's, my favorite example is the online notepad. If you go to Google and search for online notepad, I guarantee you're going to find at least 60 to 80% of those are vulnerable to persistent XSS. You can just throw arbitrary data into it. And if you can create like an API in JavaScript that actually allows you to go out to disparate hosts, using iframe communication or JSON-P if you can, and come back and send the data back to the client, you can actually have a shared storage medium that all the clients, without even having a router, will be able to communicate from. I mean, obviously this is going to be a lot slower than having a persistent URI connection or a connection to a router. But if you're really worried about that sort of thing, then maybe you can just completely disassociate yourself from the router, use clients as routers to mingle stuff together, and yeah. So if you want to talk about this more, we'd love to talk about it. But
exactly, we're running low on time, and I want to leave time for questions as opposed to other cool ideas we had to extend this. You can continue to look at the slides, but the one thing I did want to say. So when we were talking a lot about this, thank you, 10. So we talked about WikiLeaks and some press examples, and we used, WikiLeaks is an amazingly valuable service where people can post stuff. And we made, unfortunately, some misinformed comments where we said, well, it's a single point of failure because someone could subpoena them, whereas a darknet's decentralized. We really were trying to focus on the decentralized part of it. And we really did them a disservice because they've done a tremendous job creating an infrastructure from the OS level through the web level that avoids collecting user data and avoids collecting logs. I was talking with some folks at the speaker party last night, and they're saying, look, there's nothing to subpoena. Even if they got one, there's no data to give them. So it's a great service, and we certainly didn't want to make it seem like they sucked, and what we have is the solution to why they suck.
We're not trying to say that at all. So yeah, want to open up for questions? Anything you guys want to talk about? Yeah. Thanks for listening.
You guys aren't releasing the source code. Is that because your employer won't allow you to, or
It's we're lazy. No, so HP has been extremely supportive of our work. Seeing as how they it's oftentimes very shocking what we're allowed to get away with. It really came down to the process of going through and releasing intellectual property created by a Fortune 15 technology company to the public is a very long process. And we kind of looked at this and people said, look, the easier thing to do here is just give a highly technical talk and try to share as much information about how the system works instead of actually going through the process and the hassle of actually being able to release the code. And we thought that'd be it would just be easier. Yes. Any other questions? Yes.
Have you guys given any thought to a node that's both a client and a server? Like maybe using something like Opera where it's got a built-in web.
Good question. Yeah, so in the ideal world, we move exclusively to peer-to-peer in the browser through the client-side technology. Right now, because of same origin and some of the problems, we haven't been able to do that. I would love to see that as an advancement.
Yeah, we just need some server-side scripting on the Opera Unite, and then we'll be good to go.
Excellent. Yes? Sure. So first of all, we used a lot of code. We stood on the shoulders of giants. We did not write our own crypto libraries. We grabbed, I think, MooTools we used to abstract out, or maybe it was Dojo storage, to abstract out, are you writing to the WAT working group client-side database? Are you writing to Google Gears? Because one of our demo things, Chrome has Gears built in by default. Yeah. Or whether you're using, say, local or global storage. So we used something to abstract that for us. MooTools, Dojo.
We use the Yahoo, the UI that Yahoo releases.
Yeah, their UI for their web toolkit, or for their UI to make Chrome look pretty.
All of the encryption stuff was PidCrypt. All of the storage stuff was kind of a combination between Dojo storage and another one called Persist.js.
Mm-hmm. Excellent. Any other questions?
Yeah.
So we only scaled this to about 10 or 5 to 10 supernodes, where we had servers scattered around the office actually running the PHP file and connecting. And it started getting very noisy. We were on a LAN, but it was really difficult to look at those Ethernet captures.
Yeah, we're not really trying to go for the super large network. And essentially, we're just trying to say, hey, let's try to create a medium-sized network that really kind of focuses on something that can be built up quickly and torn down really quickly as well. And that's where we really see the benefit of like a browser-based darknet. Right.
Your scalability problems start coming in with supernodes. Right. It's really easy to have 50 nodes connected to a single system. I mean, that's what Twitter does, basically, with their using Ajax to poll and get new messages, or what, say, Meebo does, where everyone connects to Meebo.com and they're using Ajax and talking just to that one system, or GChat. So that scales really, really well. And you can just throw hardware at that problem. But when you start having multiple supernodes and those are connected in various kind of hook and wheel patterns, you can start getting into scalability issues.
Yeah.
You could, again, it's the whole thing that a darknet's a private network that you said, hey, I want to opt in and join this. Now, just the same way you can, opt in to saying, yeah, I want to be available for private chat, so go ahead and make my public-private key. Like, broadcast that I'm someone who can provide a public and private key. We added a feature so you could say, hey, let me be available to do other people's jobs. So yeah, you can kind of control that. But it's a switch. It's not like I'm okay with these types of jobs, but not these.
And certainly, since it's all client-side code, if you did not want to be a party of certain parts of the Darknet, you just X that out when you're running it. So
yeah, Firebug and just stop it. Yes.
So it sounds like you have kind of an inherent flaw that would allow somebody to kind of accidentally create a denial of service and shut your Darknet.
Excellent. This is why we wanted. This is what we want to hear. What is it?
Well, I mean, if somebody knocks on the door and they don't recognize them, and just go, oh, okay, well, we're going to shut down in 30 seconds.
Sure.
It seems like you can just broadcast out and say, hey, this guy wants to get in, I don't recognize him.
Sure. But how do you know where all the supernodes are? Like that's only good. So it's kind of like you could denial of service a private club if you knew where all the doors into the building were. But if I have a supernode in Atlanta and I have a supernode in California and I have a supernode in Germany and I have a supernode in Japan and they're not tightly coupled, they're fairly loosely coupled. So the one in Japan's under attack. Unless the person who's trying to bust into the one in Japan knows about the other ones, when the Japan one shuts down, what are they going to do? Like you can't. That would be, I mean, I guess you could write a crawler that crawls the internet and on every page it finds tries to look for a signature and break in. But unless you know where the points are, you have nothing to launch the attacks against.
yeah, and even if it was an insider, the great thing about the browser-based darknets is you can just take it down really quickly and then go get another server somewhere else, throw the PHP script on there, and you're good to go.
Yeah, as we wind down, kind of the key takeaway points here, we're not trying to replace the darknets that exist. There are some really great ones. There's just the barriers of using them are larger than most common people can afford in terms of technical sophistication and just knowledge of them. And so we said, look, with HTML5, the fact that these JavaScript machines are so fast, the fact that they're allowing us to do some cross-domain communication, the fact that we can allocate megs, if not gigs of space on the client-side database that we can then share. Can we build a system where we can redundantly share files, have some type of chatting system on top of this, and as Matt pointed out, make them very easy to tear up or to bring up and tear down? And the answer is yes. And we're like, wow, this is kind of cool. What can we do with this technology? And we don't have the answer to that question. That's the question we have to you guys: is what can you use this for? What do you see this as valuable? I think the using file caching, HTTP caching, to do massive storage on a client is kind of a cool application that outside of darknets would have some interesting applications. So I think there's a lot of stuff you can take from this presentation that doesn't have to do with darknets and apply it to other problems. Yes?
But if you have an insider who actually connected to the supernode and is technical blog post, will all this be rewriting to the next point?
That is correct. So basically, it's kind of like saying, once a pyromaniac gets into the club, yeah, he can burn the whole thing down, no doubt. So because what he'd do is he would go, oh, I'm connected to this supernode, and I know about these two others. Great, kill this supernode, switch to this guy, find out some more, kill him. So yes, that is possible. But as Matt said, you just create a new one somewhere else.
So we've run out of time, but come up after and ask us some questions. We'd love to talk about it more. And thank you all for listening to our talk.
Thanks.